All right, recording is rolling. It is Wednesday, August 14th. Here's our agenda today. Back on Monday, I had a PowerPoint for you guys, and I was starting some questions that you guys are going to see throughout the semester and the year. So I did want to go hit those just to plant some ideas that you're going to see along. I want to go over the silver banner posters that there's a lot of background fundamental content that you guys can see in this class, scientific method, how to think in science terms, basic measurements, so basic math that you probably had classes for, algebra, geometry, trigonometry, right? You're going to see over and over in this class foundation. AP classroom update. So I've got 24 students, 17 of you guys are signed up. I did open the first two assignments, but they're not due for many weeks from now. Right? So but if you want to hop in, maybe this weekend you can go explore what kinds of questions are going to be coming up over the next few weeks. That can hurt you. Okay. And then on your desk when you guys walked in today, I see some of you guys already chugging away on this. I've got all these algebra questions. Hopefully you guys can do these. If you're a little bit rusty on these, I might do some of these with you guys. Okay. Now, this is really just a practice page. I'm not planning on grading this, but wanted to kind of leave it up to you guys. So if you solve like 10 of these and I go, all right, knock these out of the park, then you know where you are. If you're really struggling on these, then you know that too. And you've got plenty of practice here. There's 40 questions. You can ask each other. You can ask me for help. Okay? But the flip side of this, you guys see if you look on the other side, there's 10 puzzles related to this right triangle here. Okay. Now this I'm eventually going to pick up from you guys. I have a tentative due date here of Tuesday the 20th. Yeah, trying to kind of pace things out. Yeah, so let's do that. Go ahead and write that in your planner. And then if that ends up not being enough time, then I can always bump that back. Oh, yeah. Tuesday the 20th. Okay. Oh, yeah. You guys got your planners. You see you guys got your planners out. Okay, that is awesome. If you don't have your planner for whatever reason, I've got some scrap paper on these two stools. So you can make a makeshift planner for yeah, right. Yeah, so Tuesday the 20th, right here. Tuesday the 20th. Right. So I do have this is one of the slides in the PowerPoint today to cover how to solve some of these, right? Can you work your way around a triangle, like right triangles? You're gonna see this all over the place in physics. Right? So the earlier you know this, and the better it's gonna help you. If I give you a right triangle, I give you a little bit of information about the triangle, say a couple of details, right? Then you figure out everything else. Right? So I've got 10 puzzles here. Each one of these could be a unique situation. Actually, each of these deals with vectors. So I put some unit, like in this meters, in this newtons, like a push or pull, like a force. Right? So you can start getting familiar with that. All right, so you guys good with kind of what we're doing? All right, so here, let's go back to the top here. Let's finish some of these questions from the other day. Okay, share that screen. Let's do. All right, I think it was approximately on this slide. Okay, all right, if there's a little bit of overlap, then over here. All right, so suppose you're, and again, I just want to throw these questions out there, just have you guys think about them. Maybe you know the answers to some of these, maybe not. All right, suppose you're sitting in an elevator. The elevator takes off. Right now, when it starts to move, you feel the floor. You can definitely feel the floor move, like whoa, right? But then what you'll notice is you actually feel completely normal for a while, right? While the elevator is in motion, probably nearly impossible to distinguish from just being at rest, right? But when the elevator comes to a stop, it's like, whoa, okay, I can feel it again. Right? Suppose you're standing on bathroom scales, you can actually get some numbers. You can quantify this, right? That scale is going to show your weight shifting around. What can that tell you about the motion of the elevator? I guess in this case, it's like speeding up or slowing down. You're an engineer. You're designing a truss bridge. How can you determine the tension or compression in any part of the bridge? And kind of the extension on this is the engineering application of maybe you work for a company and you're going to the government wants a bridge, right? So the government's going to order a bridge. They contract out, say like 3 different companies, and they're looking for like the lowest bid. Right? How can we get the bridge that we want for the least cost, right? Okay, well, if you're designing this bridge, see, I don't want to make one part of the bridge like super strong and another part super weak because, all right, it's obviously going to break the weak part. So okay, let's fortify that. But the part that's super strong, well, maybe we kind of like overbuilt that. Now we've got too much materials and too much money going into that part. Right, so that's kind of a waste of resources, right? Right, so but how am I going to figure out? Right, so I need to know something about the materials, but I also need something about the compression or tension in each part. Right? What's the longest straw that can draw water on Earth? If you had a straw that was like like 20 meters tall, right? Could you could walk outside a skyscraper and like, ooh, I see a cup of water down there on the sidewalk. I'm thirsty. Like lower down a 20-meter straw. Is that going to work? And why? What would be the limitation? Huh? Maybe something to do with atmosphere. Okay, that's a kind of a weird phrased sentence. But here, what about this? What if you put a textbook on your desk and you start to tilt the desk? You think if you tilt it like 5 degrees, the textbook will stay stuck to the desk? Probably so, right? What about 10 degrees? What about 15 degrees? At some point, it's going to break friction and slide off, right? What does that have to do with the properties of the book and the desktop? What if you replaced your slick desktop with like sandpaper? Right? How would that change that angle? What's the physics there and what's the math? Right? That's a problem you're going to solve a few weeks from now, and you'll have to definitely be able to solve for AP, right? So all the orange banners, you guys have 2 pages of orange banners, so it's like 32 there. All right, so you can make your way. Actually, that last question, I think it's answered by it's the very last one probably. Okay. All right, next set of questions. So moving on later in the year. What angle would you bank a road going around a curve so that drivers can make the turn, even when the road is iced over? Suppose if there's a curve in the road, maybe what if you know like the radius of curvature, what if there's a speed limit sign that's 45 miles an hour? Okay, they're probably going to go about that speed, probably, right? But what if the road is iced over in the winter one day? It's like, probably not a lot of friction to make that turn. But, you know what? If I bank the road, how much would I have to bank the road? What does that have to do with those other properties I mentioned? Right? You guys ever? I don't know if you guys watch NASCAR. A lot of those roads are banked really, really steep, right? Because they go like 100 something miles an hour around those curves. How fast does a roller coaster car have to go through a vertical loop? See on the chat. You guys ever been on a roller coaster? Maybe one with like a vertical loop. What if that elevator like is it going fast enough through that vertical loop? Maybe fall out of your seat or the cart falls off the track. There is some minimum speed to get around, right? And then anything faster could be sufficient speed, but I get that. Oh, hey, how about satellite in orbit? Right. If you look at where satellites are in orbit in proportion to Earth's radius, it's actually not that far up. Like if the Earth was like the size of a basketball, it'd be like less than a centimeter from the surface would be the International Space Station's going around. Just think about proportions, right? Right. The gravity field up there is actually about 90% of what it is down here on the surface, so it's not even all that different. But if you send it to the side fast enough, so how do you reach orbital speed? Like, what's the speed there? So we got these posters. Got a little bit of rotation going on. Got some triple force stuff to go. Oh, let's look at this one real fast. You guys see the one that says O'Neill cylinder? So if you have a big old cylinder in space, give it a spin, and you're walking around on the inside, you can get artificial gravity that way. So just if it's big enough and you have enough materials, right? It's hard to get stuff in space right now. It's really expensive, but someday we'll have stuff like that, right? You may have seen that. Do you guys watch the movie Interstellar? Maybe, right? They had some of those, right? Right. So and I think there's this game called Halo or something. Oh, okay, yeah. Students tell me like, hey, they stole that from Halo, or did Halo steal that from physics? And so, how fast do you have to spin it? All right. Okay. Here's some more universal gravitation. It's all related. Blah, blah, blah. Right. Orbital speed. Hey, there's the answer to that right there. Let's do some energy stuff. Why can't you have a perpetual motion machine? Right. Why does power plant need a fuel source? Right. How fast or how high can a spring fire a bouncy ball? Suppose you have. Here, I was going to do pen cartridge, but I don't want to encourage anything that's dangerous, going to poke people's eyes out. But here, I got a ballpoint pen here. It's got a spring right here. If I push down the cartridge, if I let it go, how high is that going to go? What does it have to do with the properties of the spring? How stiff is the spring? What does that have to do with the mass of this cartridge? Right? Or right, like how fast could it fire? Okay. This is a real classic physics question here. What's the relationship between car speed and braking distance? So you're driving along, say on the highway at 50 miles an hour or whatever, right? And you slam on the brake, come to a stop. Okay, so what would allow you to make the stop? Well, I know if it's a rainy day, it's probably harder to stop. Maybe something to do with something between the tires and the road, right? And here, this question has to do with what's your speed. So what if instead of going 50 miles an hour and you brake in some distance, what if you doubled your speed to 100 miles an hour? Okay, and we'll maybe spoil this a little bit. It turns out that double the speed does not correspond to double the distance. It's actually a different type relationship. I wonder what that is. Probably good to know if you have a license, right? So, how can you amplify your physical strength, get a mechanical advantage with the pulley system? Oh, yeah, I got this right here. So, if you watch this video at home, then maybe use your imagination a little bit. Which I think I may put this on the next slide, but I got this right here. You guys notice? I got 2 weights on this pulley system. You guys see a small weight here and a relatively large weight here? You guys see that? Right here. If you let them both go, which one's gonna fall down? The small weight or the big weight? Oh, look, those small guys look to the big guy. Huh. Right. So if you were on the side of the small guy, you're like pull up, you like pull up a grand piano. Huh. Right. You can lift something very heavy with a small input force. How are you getting that mechanical advantage? Simple machines. Is that? Oh, there it is. There it is. All right. So if you're watching the video, then there you go. That's exactly what I got rigged up right there. Okay. In a little spring scale, so you can even see how much force. All right. So all these green banners, right? That's all related to those. Right. How can you determine the firing speed of a bullet by firing the bullet into a pendulum? Suppose it's like the year 1888, and we just release the whatever revolver, and yeah, how fast can this thing fire? Hey, also see that pendulum over there with a block on it? Let's fire a bullet into that pendulum and just see how high it swings up. And there's enough information there. Say if you know the masses of all these things, we can answer that question. Called a ballistic pendulums. That's fun. Speeds and directions. Well, hey, billiard balls move after being struck by a cue ball. Right? So you might get good at billiards, pool, right? Physics involved with that. You might notice both of these questions have to do with collisions, right? Collisions, you guys see? Right. So it's running theme in this section again. How high will a given ball rebound off a tile floor? Oh, there's another collision. Right. So you drop a tennis ball, you drop a basketball, you drop a bouncy ball, and it rebounds to some height. What's the physics going on there? Right? So all these blue banners, anything to do with collisions, the property here we're looking at is momentum, mass times velocity, if that. Okay. And I think this is the last set of these questions here. Ooh, tightrope walkers carry, okay, hold up their hands or carry horizontal, pulse horizontally, maybe I should say. Okay? Or maybe you, have you guys ever tried to balance on something? You guys hold your hands out like this, right? What does that change? Does that change your mass? You know? Does your center of mass actually change location? Huh. I think it's the same location, but there's there's some physical property that changes. Think about that one. Ooh, ice skater. I know you guys probably watch Summer Olympics, but in Winter Olympics they have the figure skaters, right? And so they'll go into rotation, pull their hands in, speed up spinning. What the heck is that about? What's the there's a conservation principle, conservation of angular momentum. Talk about. Ooh, tensions and scaffolding and ropes. Suppose you got like some big board to walk back and forth and being held by a couple of ropes, right? You guys think if you walk to the left end, the left rope gets more tension in it, and you walk over to the right end, the right rope gets more tension in it? Right? And what's that have to do with your own weight and your location as you're walking back and forth? Right? What else I got here? Oh, suppose you got a roll race. What have I got here? A bowling ball on a frozen can of soup. You let them both roll down hills. They're not going to tie. Somebody's going to win that race. If there's static friction, that is, right? That's all these purple banners. All right, so I got, I think 2 pages. Yeah, there you go. 2 pages. Oh, hey, look, there's the roll race right there. Bam. And why would any of those, why would they come in that order, right? Playing that race, right? All right, that will take it. That's, okay, so everything I just showed, all those thumbnail notes, those were all in that plastic sleeve. You guys all got plastic sleeve, right? That'll take us to December, right? And then we've got some more stuff to do next semester, but that's all the way to December. All right, you guys also have a couple pages that look like this. So here's, I think almost all the variables and units that you guys are going to see in this class, and they're roughly in the order that you'll see them in this class, right? So you guys see variable x or delta x, it could be a position or displacement, right? And it says what unit. What do you guys think M stands for? Meters. Yeah, meters as a unit. Right? Now, careful, because if I skip down a bit, oh, look at that. M as a variable, not as a unit, but as a variable. What do you think M stands for? Mass. And that can be measured in, what do you think kg stands for? Kilograms. Right? I got one right here. Guess this kg, this kilogram. Here, kind of lied to you guys. I got 2. Not counting that one. I'm gonna pass this around so I can get the idea. You guys can get the feel what is 1 kilogram like. Now the English type equivalent English unit is it's about 2.2 pounds about. But the metric system actually handles mass and weight better than the English system. So we'll talk about that too. Anyway, so yeah, so be familiar with these. Like the more you just solve physics problems, you'll be more familiar just by using these. Right, but there you go. So you got 2 pages of variables and units. Actually, the second page, there's some stuff not going to show up so much on the AP exam. Like all the electricity stuff is not on AP, but I'll do a little bit with you guys just so you're familiar with it. All right, there you go. So you guys got those. You guys got 2 pages of grids that look like this. I've been using this as a review page for a few years now. And so show you guys the structure of this. Do you guys see each row is a different topic and they're roughly in the same order? We're just looking at all those thumbnail notes. So like kinematic motion, dynamics, circular motion, gravitation, energy, momentum. All right, so you guys see that? Right? And then going across each column. Right? Okay, so I see the main idea on the left. Right? A question I get a lot is like, if you get some AP question out of the blue, because they're all scrambled in all different order on the exam, right? How do you kind of know what framework to think? How do I know to think in terms of momentum rather than energy or something like that? So here I put like some key flags, like, okay, well, if you see like these things, you probably have to think like in terms of this framework. Some key formulas, some key examples, at least 2 examples for each one they try to fit in. And you're going to see graphs all over the place in this class. I draw lots of graphs. There's a couple of graph examples. Yeah. Ooh, great question. On the exam, do you get formulas? Ah, that's the next slide. Oh, what a perfect question. There you go, because there's the answer. Yeah, you're going to get, actually, this one's a little outdated because the new one, I know they got rid of all the electricity questions or all the electricity formulas, but this I also printed for you guys. This is one of your printouts. You'll get one, it doesn't have the electricity. Actually, you do need to double check the new one because I know they're putting fluids in there, so there might be a couple of fluid formulas maybe, right? But it looks pretty close to this. Right, so some of the first stuff we'll be doing are these 3 kinematic formulas, right? And then, here's Newton's second law of motion, and then kind of goes on from there, right? Right, so yeah, so you can use this during the exam. Okay, so quizzes and tests in this class. Yeah, let me mention that a little bit. So what I've been doing since the pandemic is giving guys mostly take-home quizzes, and that's worked for pretty good for a number of reasons. I think I want to mostly do that, and maybe I'll have every rare once in a while, maybe every few weeks have an in-class quiz. But yeah, that's probably a good idea for AP is to let you guys have access to this because you will have access to this on the AP exam anyway. Right. So yeah, so good paper to have around, and that's probably a good idea. Yeah. Right. All right. All right. Speaking of AP a little bit, here's a bunch of AP exams. This is data from 2018. So a little bit. Do you guys know what is the AP exam with the lowest pass rate? Ooh, you're sitting in it. AP Physics 1. You guys can see it here, right? So the dark green bars is who's getting a 5. The dark red is who's getting a 1. Okay, so you guys see that, right? Right. And you have to get a what to pass? A 3. 3 is passing. Okay, so you guys got that. Yeah, I think this test is actually entirely completely fair. But okay, but you guys see what the challenge is going to be, right? Okay. All right. And I also want to give you guys scores from this class from last year. So how the students sitting in this class last year do. So here we go. The global average pass rate on this test last year was 47%, for Florida 44, and students in this class collectively just over half, right, 51% ended up passing. And this is what the breakdown looked like. Again, for like your peers, they're probably still going to the school, right? Or a lot of them right, haven't graduated yet because mostly 11th grade, right? So 4 students got 5s, 5 students got 4s, and then yeah, right, so looking pretty good overall. Actually, that's the best year I had so far, so it's pretty good. All right, let's go ahead and hang up that PowerPoint there because I want to move on to let's do all this scientific method stuff. All right. So scientific method, different textbooks have slightly different versions of this, so I'm just gonna pick one and run with it. What do you guys think might be a good first step of the scientific method? Yeah, okay, yeah, all right. You guys saying question. Right, so some kind of question floating around, right? Maybe I should preface too that here I'm gonna outline the scientific method. It's very textbooky, but science works all different ways. There are definitely exceptions to the rules. Sometimes here I'll give you sort of a counterexample to that question is maybe like the discovery of penicillin, right? It was just complete accident. There are complete accidents all the time in science where it's like you make some discoveries, like you just kind of stumble upon it. You don't even know the question's been asked, right? Right. So we've got some target question in this class. A lot of times, like what's the relationship between this variable and this variable? And by the time you get to the conclusion, make sure that you're answering whatever question was being asked. Right? You've seen plenty of lab write-ups where you get to the conclusion. It's like, wait a minute, do you even know what was being asked? Okay. Whoops! I was going to ask you guys. Is that? That's. Okay. I'm gonna test you out, but maybe some kind of background research is oftentimes maybe a good second step, right? has this question been asked before? What were people's thought process before? What's kind of the open availability of possible outcomes to whatever question, right? What conclusions do other people come to? What do people kind of know about this? What do you guys think is going to be next step? Hypothesis, boom, hypothesis, right? Is that like an educated guess? Okay, so I think this might be how this works. If you can have it as an if-then statement, that's pretty good. If you can quantify it somehow, make it more specific. How about this? Ooh, I got a good hypothesis question for you guys. Guys, what makes a valid scientific hypothesis? Let me see, show of hands. Give you guys a couple options. Should your valid scientific hypothesis be something that is only ever verifiable or only ever falsifiable? Who thinks, show of hands, a correct scientific hypothesis can only ever be verifiable? Who says falsifiable? Oh, look at you guys go. Yeah, you guys got it right. Falsifiable. Right. You have to put out something that can be tested, that can have holes poked in it, that can possibly be wrong. Right. Give you guys a little example. Suppose you work at a soda company. You want to figure out what's the correct amount of soda or sugar to put in the soda. Okay. So you take a few sips, a few samples, you go, okay, I'm going to guess like 15 milligrams. Okay, so that's your hypothesis. I think the optimal amount is like 15 milligrams. Okay, now let's do a wider study. Let's get like 200 participants. We'll line them up with all these sodas, and we'll put on a gradient. We'll do 10 milligrams, 11 milligrams, 12 milligrams. Let's take it all the way up to 20. I think the answer is going to be 15. Let's go 10, 20, right? And then you put together a bar chart and you see a bell curve emerge, and maybe it peaks at like 13 milligrams. Oh, okay. Well, it was like the most popular. So if we want to sell the most soda and make most people happy, we'll have to, like, the optimal value ends up being 13. So great. I just falsified the 15 milligram hypothesis. I thought it was going to be 15. Oops, I was off a little bit. I falsified. Okay. It's something you can test. Right. Oh, what do you guys think the next red apple is? Experiment. There you go. There's the heart of the scientific method, right? So get some materials together. One of the free response questions you guys have in AP is to design some experiment. So there'll be some question they'll give you as a free response question. And they'll say, take some of these high school measuring tools, or maybe you have to remember what those are, right? And how can you design some experiment back in those lab tables that could answer whatever question? Okay, so we'll do plenty of analysis. So this could be, so now you get all your data. Now you have to crunch your data. There's one of two things you're looking for with analysis. It might be equations, or it might be graphs, or maybe both, right? One or the other, or both, right? Equations or graphs. Okay. And then what do you guys think? The very last one is conclusion, right? And remember, make sure that you're answering whatever question is being asked to start with, right? And okay. All right. What are ways we can measure things? Actually, let me go to. Let's do this one first. We gotta go. Well, right. So in this class for the first semester, these are like the 3 base SI units that we're going to need. SI is System International, so international system of units. We're talking about the metric system. Okay? Do you guys know where does the metric system come from? What country? France. France in what year? Approximately what decade? Let's go. You guys heard of the French Revolution? Yeah, like 1790 is about. Yeah, so approximately that time period. Right. So yeah, they said, well, we're revising our entire government society. Want to make it look more like the Americans if we can. I did, right? Then yeah, let's come up with a standard system of measurements too, right? Because at the time there were weird standards. There was kind of non-standards, right? A lot of people were like using like palm of their hand as a measurement. How do you like write that down on paper, and so maybe 10 years from now in a completely different place with a completely different hand size looks at how they replicate exactly what you're doing. Okay, so let's come up with stuff that's based on base 10. It's logical. We'll scale everything up down by factors of 10, right? So you don't have to have like there's 4 quarts in a gallon, there's 5,280 feet per mile, all these weird conversion units. But let's just do everything base 10. Okay? Right, so what was the original definition of? I passed around a kilogram. You guys are filling in what is 1 kilogram. Now that's 1 kilogram of mass, right? So the original definition was that right there. If you took 10 centimeters by 10 centimeters by 10 centimeters, so that's maybe a little bit bigger than a Rubik's Cube, right? And fill that with water. Gloop, gloop, gloop. And, okay, so put that on a scale. There's 1 kilogram. That was the original definition. Now the modern definitions of all these things are tied to universal constants. They try to get away from physical objects, but that's where it comes from, right? So that's 1 kilogram. Okay. But what is a what is a centimeter? Okay, so okay, I know there's how many centimeters in a meter? Yeah, 100, right? Right here, I got a meter stick right here. Here's a meter stick. It's a little bit longer than a yard, a little bit longer than 3 feet, 3 floor tiles, a little bit longer, right? Right, and okay, so I see 100 centimeters on this thing, right? 100 centimeters, right? But what was 1 meter? So okay, let's try to come up with something pretty universal you can get, you know, anywhere in the world. Let's go from the North Pole down to the equator, divide that into 10 million parts, and that was the original definition of this thing. Again, the modern definition is kind of universal constant, so it's how far does light go at light speed at some tiny, tiny, tiny fraction of time. Okay. Yeah. Yeah, it's related to that. Right. Right. And then okay, so what is 1 second? So the original definition, if you take 1 day from noon to noon, right, divide that into 24 hours, divide that into 60 minutes, divide that into 60 seconds. Right? They try to, again, like back in the 1790s of France, also make that base 10. Let's have 10 days in a week. Let's have 10 hours in a day. Right? That one didn't really stick. So that's the only one that's exactly aligned with like base 10 stuff, but there you go. Okay. The original definitions. Okay, no, we're going to take those right there, kilograms, meters, and seconds. We're going to mix match those every way to create a bunch of other units. Right, so, oh, here. Right, so, like for example, a force is just a push or a pull. If you push or pull on something, that's a force. We're going to quantify that in newtons. You might think pounds, but okay, here's the tricky thing with pounds. In the English system, pounds is used for both mass and weight, although those are completely different concepts. Like mass is how much material, how much inertia something has. Like here, I passed around that kilogram mass, right? If you put it on your desk and you push it back and forth, like roll it back and forth, right? However hard it is to change its state of motion is related to mass, right? But if you hold it in your hand and you feel the earth pulling down on it, that's a force. That's like weight, right? And pounds versus pounds, this gets really icky and really weird. But in the metric system, we're going to quantify mass in kilograms, and we're going to quantify force in newtons. Okay. So if you go to the moon, here, let's see if you guys follow what I just said. Suppose you take that kilogram mass that's being passed around, and you take it to the moon. Is you like have a table, and you set it up, and you push it back and forth on the moon? Is it equally difficult to push it back and forth on the moon? Yeah, feels the same. Good. Does it still have 1 kilogram of mass? Yep. Right. But what if you hold it and you start lifting it? Is there still is the same weight? Is the same gravity force pulling down? Not at all. It's a lot less on the moon, right? So those are different concepts, right? Here, I'll tell you guys what 1 Newton of weight is, right? 1 Newton is 1 kilogram meter per second squared. That'll make more sense here in a few weeks, right? But kilogram is the only base SI unit that has the prefix built into it, because kilo could be 1,000, right? So it's like 1,000 grams. Gram is about a paper clip, right? Something like that, right? But this is like a base ingredient that's going to go into more complex units later on, okay? Okay. You guys going to see energy in joules. That's kilogram meter squared per second squared. You guys can see power in watts, kilogram meter squared per second cubed. It's going to make a lot more sense as the semester goes on. But these are like the 3 base ingredients for everything you're going to need here to December. Okay. Okay. All right. Let me go back to the last slide that I skipped here. All right. Oh, or maybe I should ask you guys, can you guys think of anything you could possibly measure that would not be covered by these 3? Ooh, that's a good idea. Okay, so like how loud is sound? Now let's wait related to either pressure or intensity, which interestingly enough, actually you can relate back to these. Right? There you go. Okay, so how bright is something in lumens? Yeah. That's actually that you can tie back to these too. Yeah. So you guys are saying like how bright is something? Okay. Okay. Now radiation you can put in watts. Interesting. Weirdly enough, you radiation in watts you can tie back to just these 3. Weirdly enough, right? But if you want to say like how bright is something, you can take that right in like watts and you can convert over to lumens. Right? Here's the full list. Right. So we got kilograms for mass, meters for length, seconds per time. Okay, so we got those 3. Okay? Those are the main 3 you care about. Electric current could be in amps, amperes. I'll touch on that with a little bit with you guys, but it's not going to show up in the AP exam. How about how hot or cold is something? I'm going to put Kelvin on here for an absolute scale. Go Fahrenheit, Celsius, it's a similar idea, but you stick to Kelvin. We'll talk about that. Yeah, you guys were talking about luminosity. No, you guys said lumens. There's a similar idea called candelas. It's a little bit different, but they're related to each other, wanting to figure out the other.
And if you're coming from chemistry, you probably learned like a mole, or it's just a giant number, right? So you probably learned like a mole, or it's just a giant number, right? So just like counting. Okay. So there you go. Yeah, you can take anything and everything that we know how to measure. Comes back to these right here that you can, right? And there might be things that we don't know how to measure, right? So there's question like interesting question of like what about like consciousness? Is that something that's quantifiable in some way? And how would you even begin to measure that? And does that have anything to do with these, or is it something that we have no idea how to tackle, right? There's still questions out there, right? All right, measuring tools, right? You're gonna definitely want to be familiar with this. You guys, AP, because AP exam, you're gonna get a free response question. We're gonna have you design a lab, right? But you'll be familiar with these anyway. So here's a big picture list, right? So you want to measure displacement. We got meter sticks, we got rollers, so you guys know those, right? You can measure meters, centimeters, right? I got a protractor here. You can measure angles in degrees. A lot of times we'll be using. Guys, what's another way to measure angles other than degrees? Good, radians is a good way, right? Actually, radians is a more mathematically pure way to do it. It has some advantages, but okay. But we got protractors and degrees. You can also do revolutions if you like. Okay, stopwatch. I got a box of stopwatches back there, so you can measure how much time has passed, right? Probably a lot of these easy to take for granted, right? I mean, we just like live with like time ticking, but I mean, it took people like thousands of years to even come up with these ideas as concepts, right? Oh yeah, there is such a thing as passage of time. I have some motion detectors. You can see how far something moved, how fast it's going, and also the rate change of how fast it's going, like speeding up or slowing down, called acceleration. Ooh, I wonder if that's what you could feel in a car. Maybe that's what it is. How can you measure how massive is something? So I've got digital scales. Do you guys know triple beam balance? It has a plate, like balances out. You guys go to the doctor's office, they have a kind of a version of that, right? No, those actually work differently. Like the digital scale actually measures a force on it, like a gravity force, and then divides by Earth's gravity field to say, okay, well, what mass would it produce? Blah, blah, right? But the triple beam balance, here, let's say we take both of those tools to the moon, right? So we measure on Earth. You guys put the 1 kilogram mass on there. It's 1 kilogram. Okay, 1 kilogram, 1 kilogram. So that's all good, right? You take them to the moon, right? Guys, if you have a scale, like a bathroom scale, you put that kilogram on the bathroom scale on the moon. Is it still going to show 1 kilogram equivalent of mass? No, because the weight's all off, right? Even though there is 1 kilogram there, but it's really reading force, and then it's telling you, okay, right? What about triple beam balance? It works on a like a leverage principle. If you put a 1 kilogram mass on a triple beam balance on the moon, it's working like a seesaw sort of, right? Yeah, exactly. Yeah, it's relative. So it'll still give you 1 kilogram. Yeah, so that's still accurate on the moon. Okay. Spring scale. Oh, do I have one here? No, you guys probably know a spring scale. It has a spring in it. You can pull on it. Oh, actually, sorry, thank you. I do have one. Right, this guy right here. Right, so it has a spring in here that's some stiffness. We're gonna quantify in Newton per meter, and then the more you pull it, it takes more force to pull it, and then there's a scale that tells, if you know how far you pulled it, how much force is. Okay. A force probe. I don't think we'll be using, but sometimes you see that in AP write-up. You can push or pull on something. It also tells you how much force. Again, we're going to quantify that in newtons. And these last two, we might hit a little bit. So do you guys know like a AA battery? It has like some electric potential in it. It has like, do you guys know how many volts that is? A AA battery? It's like 1.5 volts, right? Get a bigger boxy battery, it might be like 9 volts. I think your car battery is like 12 volts, right? Once like push electricity through, right? Then how much electricity is actually flowing. You can measure that in amperes with an ammeter. Okay, right, there you go. Right, most of these that you guys are seeing are on those thumbnail notes. Right, so you guys have those. There's a couple that are not on there, right? Universal constants. So you guys remember the definitions of all these units like kilograms, meters, and seconds. They try to switch away from physical objects to universal constants. Actually, just completed that a few years ago, that whole project of switching over to universal constants, because now these are the same like everywhere in the universe, right? There might be like 2 on here we end up using in this class. So universal gravity constant, you guys see that big old G right there? We're definitely going to be using this, so you'll definitely see this. And possibly the speed of light, you guys might see here and there in this class. A lot of these other ones, no. This is kind of a bonus poster, so you don't have to like memorize a lot of those anyway, but maybe made this because I want you guys to kind of be aware of just the idea, right? Because nobody knows why these numbers are what they are. And that's a mystery too. Like, why is the speed of light what it is? And what does that mean? Why is the universal gravity constant what it is, right?
Right. Yeah, so more I could say on these, but I'm gonna kind of skip along here. Okay, that's good. All right. Scientific notation. So here's how you can express very, very large, very, very small numbers in a more convenient way, right? So say the mass of the Earth is like 5972 and like a string of zeros. There's I think there's 21 zeros following that too, right? Guys, what's a more condensed way you can write that number? Yeah, try it out. You guys got your notes out, right? Here, write that number in scientific notation because I put some animation on the slide, but before I show you guys the animation. Okay. Write that number in scientific notation. What did you guys just write? 5 point what? Here you go. 5.972 times 10 to the 24. You guys got right because there's 21 zeros and then 1, 2, 3 more places, right? So okay, so that's what you should have written. If you wrote that, then you know what you're doing. Okay. If you didn't write that, then well, gotta know how to do that. Okay? So the rule is I'm always putting the decimal in front of the ones place, and then I'm going to restore the decimal place. In this case, you had to move it 24 places. So it's like, okay, times 10, times 10, times 10, or you do like 24 times. Oh, well, that's what a power is. That's 10 to the power of 24. Okay, so you can just slide that means slide the decimal 24 places. Okay, you guys got that? Okay. Another thing too is this tells you how much precision you have. Because guys, all these zeros, are these actually zeros or are they just placeholders? They're just placeholders, right? Like, do I know that this zero is actually zero? Well, probably nobody knows what number actually goes here because how do you even measure that precise, right? So especially at like 4 digits of precision, you can express that here. But what about this zero? You guys see this zero right after the 2? I mean, maybe we possibly know that level of precision, but it's kind of ambiguous when you write out the number full length as to what zeros are actually significant and we actually know, and which ones are just placeholders. But here's another advantage of scientific notation is you can know in scientific notation what's significant or not. The way I wrote it, it would not be significant. It's just a placeholder. Now, if I took my time to write a 0 right there, right, now, would that be significant? Yes, because now I would be writing a 0 in the scientific notation right here. Okay, you guys got that? Okay, all right, something like that. Plus, it's easier to put in the calculator if you have to do a calculation with that, right? Mass of the Earth. Bet you're just going to use that at some point. Mass of a proton, 0.00. There's a bunch of zeros before you get to 1673, right? Because what's the exponent for going the other way? Negative exponent. Guys, does a negative exponent make the number negative? No, it's like divide by 10, divide by 10. Like 10 to the power of 1 is 10. 10 to the power of -1, that's like 1 over 10, right? Like you're dividing by, okay. And then you do that like 27 times, that would restore the decimal place, okay? Right, so you guys got negative exponents, okay? Right, you guys got scientific notation, right? This is, again, one of your thumbnail notes, like most of these are, right? Right, so kilo is 1,000 of something, milli is 1 over 1,000, like a millimeter, little tiny, right? You just tell with your eyes, that's 1/1000th of that meter stick, right? Okay, right, so there's 1,000 dots. You guys can kind of get the idea. Okay, good to know. How about some other prefixes? Okay, these can be kind of good to know, right? Do you guys ever learn a mnemonic device with these prefixes? What did you guys learn? Because there's different ones. Do you guys ever hear King Henry died by drinking contaminated milk, or chocolate milk? I guess he's allergic to chocolate, right? Or kittens hate dogs because dogs can't meow. So there. I think the main one you need from this class is like Centi, right? You guys see Centi, right? But let's look at the next slide. Next slide, right? Here's maybe a bigger, better list, right? So these prefixes you kind of see in maybe computer files, sort of, right? Like if you have a kilobyte, so like 1,000 bytes type, right? Technically, it's a factor of 1,024 for computers, but kind of drop the 24, right? Mega, or so if you have like 1,000 kilobytes, it kind of rolls over into a megabyte, right? 1,000 of those, giga, then tera. Okay, so blah, 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 right? 1,000, million, billion, trillion. Right? And then if you go the other way, here's 1,000th is milli. Okay, so talk about that. What's 1 millionth? It'd be like micro, 10 to the -6. Like nano, you guys have heard like nanobos, nanotechnology. That's order magnitude of 1 billionth of a meter, right? And then picos, super tiny, okay? All right, so some prefixes, be familiar with those. You're gonna see probably most of those throughout the year. It's an activity I might do with you guys in a few days that involves that. We'll talk about it later. Precision and accuracy. And so if something is accurate, that means that you're getting the correct value. And if it's precise, that means, well, in terms of quantifying something, you have lots of digits of precision, right? As an example, I gave you c could be the speed of light, right? So a lot of times I'll just call it 3 times 10 to the 8 meters per second, which is true. But if you want to get more precise, I guess you can actually have lots more decimal places, right? And then what is accurate? So part of the trick of the class, like any science class, is you have some measuring equipment, and how do you know if that measuring equipment is even calibrated correctly, right? Like, what if you take that 1 kilogram mass I gave you guys? I give you guys each a scale, and then I have you guys each measure it. So many guys are measuring. Okay, I'm getting like 1.01 kilograms, getting 0.99 kilograms, right? So, okay, 1.03 kilograms, 1.0 kilograms, right? And then somebody says, mine says 1.7 kilograms. Okay, do you think that scale is accurate? Probably not, because all the other scales are showing something completely different. Okay, you guys see that? All right. Ooh, all right, here we go, here we go. All right, you guys got your note paper out, right? Notes out. Let's do this. Say you have $1 billion. You spend $1 every second. When's the money going to run out? Okay. Give you guys it's kind of a hard minute, but we give you guys a minute to solve that. Let's see who's going to get this. Oh, that paper. Take 2 seconds. Yeah. Yeah, need to show you guys that. All right. Did anybody solve this? Huh? Oh. All right. All right. I think some of you guys solved it. All right. So here, but more importantly is the process. Right. So did you guys learn this method in chemistry? How many guys have seen these railroad tracks of chemistry? Oh, most of you guys. Good, 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 good. So I'm gonna start with some given value. Let's start with $1 billion and to kind of crunch it there. So let's call it 10 to the 9. That's $1 billion, right? Notice I also have a unit, dollars. That could be a unit, right? Right. And I need to convert each step of the way until I get to okay, well, how long? That's like a time unit, right? Well, I know there's $1 per second, right? So now if the theory of why this works is if $1 is equivalent to 1 second, you can create that as a ratio, like $1 over 1 second. Guys, if the numerator is equivalent to the denominator in a fraction, what is that fraction always equal to? 1. And if you take any given value and multiply it by 1, are you changing it? No, right? All we're doing is swapping out the units. You guys see it? Right, so you guys see how the dollars goes away and we have some number of seconds? That probably could answer the question right there, although it'd be some crazy number of seconds that doesn't really make sense in our brains, right? Okay. Right, so let's keep going. How many seconds in a minute? 60. So 60 seconds equivalent to 1 minute. So as a fraction, do I want to put the number 60 on the top or the bottom? Aha, exactly, right? Put the 60 on the bottom because exactly it's attached to the seconds, so that seconds go away. Okay, now we know how many minutes this hoard of cash is going to last, right? Okay. All right, let's keep going. How many minutes in an hour? 60. Does the 60 top or bottom? Bottom again because minutes. Now we know how many hours. Let's keep going. Hours in a day. 24. Now we know how many days it's going to last. Do you guys think it's going to be some number of years? $1 billion is probably going to last, right? Bing. 31 years. Nice. All right. Good job. Right, you guys can probably do that. Right. We give you guys a real hard problem. Suppose the energy demand in the United States is like 25,000 terawatt hours per year. You guys saw tera was 10 to the 12, right? And you think, what if you want to supply us all with just solar energy? I mean, this is just crazy back in the thought experiment. Right? Well, I know there's some energy coming in at some rate, right? That's called power. So let's call it, let's say it's a bright, sunny noon day in the summer. It'd be like 1360 watt per square meter. It's like, bam, just like in the Arizona desert, right? But sometimes it's day or night, sometimes it's cloudy. So here's like an average value here. And then one more consideration. Let's say our solar panels are only 20% efficient. So if 100 watts are laying in, only 20 watts go to actually useful energy on the grid, right? How much land area would you actually need to meet energy demand, right? You know, engineering technicalities aside, right? You know, all right. Maybe I kind of want to leave this to you guys. Guys, this is a really tough problem. Try this out. See if you guys can do this on a blank piece of paper over the weekend, but it takes a few minutes to think about this. So I'm going to start with a given value. So there's the energy demand, how many watts per, terawatt hours per year, right? Then we're going to go along here. So tera is 10 to the 12. This is one of your thumbnail notes. You guys got this printed, right? I know, okay, 24 hours in a day and 365 days in a year. Now, guys, at this moment, I've canceled out most of my units. Years and years, hours and hours, Terra I took care of, and days. The only unit left on the board, if you look really close, is watts. You guys see W watts? You guys look on a light bulb, says how many watts? That's a rate of energy. It's called power, right? So many watts, right? Okay, so now we're down to how many watts. Now we need to bring in the solar energy. Guys, do you want to go with maximum flux or average flux? Average, right? Because sometimes it's night, sometimes it's cloudy, right? So let's pull in 400 watts per square meter. At this point, we technically have the answer to the question because the watts goes away. Now we got square meters. So know how many square meters. Although, wouldn't that be a giant number of square meters? Guys, look at the floor. You guys see 3 by 3 floor tiles? That's pretty close to a square meter, right? Right. Getting me a lot of those. Let's do another conversion. Are there 1,000 meters in a kilometer? Now that's a linear idea. I want an area idea. So maybe I should do that twice, right? For square meters, square kilometers, right? And there's one last detail. Okay. Yeah, guys, now 20% as a decimal, how would you write that? 0.2? Okay, all right. So we get up to here. Now, if we had 100% efficient panels, then this would be the answer, right? Okay, I know 20%, that's actually 0.2, 0.20, right? Do you want to multiply by 0.20 to reduce the number of panels or divide by 0.20 to blow up the number of panels? How many I say divide, make it bigger? Because 1 divided by 0.2, is that times 5, right? Because if they were 100% efficient, we got some field size, but they're less than 100% efficient. So now we need even more panels, right? Right. So I'm going to divide by 0.2. This is the same thing as multiplying by 5. Okay. Right. And then that would, there you go. There's the answer there. Okay. Okay. There's always more I want to do with you guys, but is that yeah. Okay. That's gonna have to be our pause point today. Do more with you guys, and yeah, we're eventually working towards that that algebra trigonometry paper that I handed you guys. So yeah, when we can, be one thing at a time. If I have to bump out the due date, then I will. But yeah, okay, so we're getting there. All right, you guys have a good day.